Okay, so that is the bonding forces in solids. Okay, so bonding forces and energy bands in the solids. Now again, I have very briefly written the Bohr's model postulates on which the further continuation is there. So what was the first postulate? Is electrons exist in certain stable orbits about the nucleus, and the second one was the electrons may shift to an orbit or higher or lower energy. Okay? So thereby it may gain or lose energy. So which is equal to the difference between the energy levels. So that is the postulate says that the electrons they are present in a particular orbit. They are not only present in a particular orbit around the nucleus, but whenever the electrons shift, okay, so from one orbit to another orbit, they may lose energy or they may gain energy. And the amount of energy that is lost or the amount of energy that is gained is equal to the difference between the energy levels. Okay? So pictorially, you can represent E1 and E2. That is, E1 represents the energy level 1, E2 is the energy level 2. So whenever there is a shift of electrons from E1 to E2, okay, so the energy gained or lost is the difference of E2 minus E1. Okay. So the details of this E2 minus E1 and all we will see in the further topics also. So therefore, to start exactly with the bonding forces in solids. Okay, so here we will discuss about the various types of bondings like ionic bonding, covalent bonding, metallic bonding, and the mixed bondings. Okay, so these are the various bondings that are found in the solids. So therefore, here the basic to understand these bondings is to know that the electrons are restricted. Okay, so to some sets of discrete energy levels within the atoms. Okay, so in the earlier models, maybe in the Thomson model and all, so what was the structure? Their model was they said that it is just like a sphere of positive charge, and inside the sphere, the electrons are embedded, just like the seeds inside the watermelon. So those old models they did not give exactly structure until and unless the Bohr's model was proposed. So once Bohr's model was proposed, the picture of K, L, M and shells were also clear. And also along with that, what was the important point about these atoms was whatever the electrons were there inside the atom, they are restricted to some sets of discrete energy levels. Okay, so within the atoms. And what is the another interesting thing is here whatever energy levels are there they were not closely or compactly filled. Some large gaps were also observed, okay, so in between the energy levels where no energy states are available. Okay, and also another specification is electrons in the solids are restricted to certain energies and they are not at all allowed at other energies. Okay, so around the nucleus there are many shells. Okay, so many energy levels are there and the electrons are restricted to those energy levels. And what is the restriction on them is that electrons are confined to certain energy levels and they are not allowed to go to other energies. So therefore now a new terminology comes into picture. Okay, so what is that? Available energies or range or band of available energies associated with each electron. Okay, so therefore the electron in solid has a range or band of available energies. Okay, so the reason for having a range or band of available energies is the restriction. Okay, the restriction on electrons to cover only certain energy levels and that are not allowed to go to other energy levels. So because of this electrons are associated with a range or band of available energies. Okay, so therefore the discrete energy levels, see now the word discrete means here energy levels are not in continuous pattern, so they are like ring like structures. Okay, so that's why they are called as the discrete energy levels. Okay, and these discrete energy levels of an isolated atom, okay, are spread into some bands of energies inside the solids. Okay, so each energy level is spread in the form of different bands. So let us look at the diagrams and all in the later slides. So as of now, you imagine that around the nucleus you have the different orbits where which is covered by electrons. The electrons are confined to energy levels, and these energy levels are spread in the form of. And also one more interesting property here is, therefore, an electron in an outermost orbit is influenced by neighboring orbits or the neighboring atoms. Okay, so this is because of the presence of KLM mentions. Okay, so the electrons will go on filling starting from the K shell. Okay, and whatever the electrons are there present in the outermost shell, okay, so they are loosely bound to the nucleus. And electrons which are present in the orbits which are closer to the nucleus are tightly bound to the nucleus, and they are not under the influence of any other surrounding atoms. And whereas the electrons which are present in the outermost orbit, they are under the high influence of the neighboring atoms. Okay, now this is what is going to cause the action between the atoms. Okay, and this is what is the reason for sharing of the electrons or losing or gaining the energy, forming the bands, etc. Okay, so this is because the influence exerted by the neighboring atoms on the electrons present in the outermost orbits. Therefore, the influence of neighboring atoms on the energy levels, what it causes perturbation. Okay, it is just like a small disturbance. So this perturbation gives rise to splitting of the energy states into energy bands. Okay, so you can now imagine that before any atom comes into contact with the influence of surrounding atoms, the energy states are fixed in nature. But once the orbits, once the electrons which are present in the outermost orbits comes under the influence of the neighboring atoms, then okay, there is some kind of disturbance inside the energy levels, and that is particularly known as a perturbation. Okay, so the influence of neighboring atoms on the energy levels causes a kind of perturbation or disturbance, which in turn gives rise to splitting of the energy states. Okay, and when the energy states split, okay, so they form what is known as energy bands. So therefore here there is a one statement that due to mixing of atoms, okay, due to mixing of atoms in solids, you know that solids it has plenty of atoms. Okay, so because of the mixing of atoms, instead of a single energy level, okay, so there will be bands of energy levels formed. Okay, so if there is a single atom, it is okay, it has energy levels. But whenever the mixing of atom occurs, then all the atoms have their own energy levels. Okay, and also just as discussed in the previous slide, the outermost orbits, whatever are there outermost orbits, they are always influenced by the surrounding atoms. Okay, and because of that influence, okay, the energy levels are going to split and they are going to form bands. So therefore the reason is mixing of the atoms. Okay, so because of this mixing, once the mixing happens, single energy level will not exist, but there will be formation of bands of energy levels. Okay? And these set of energy levels which are closely packed are known as energy bands. Okay, so therefore what are energy bands? Energy bands are nothing but set of energy levels which are closely packed, and they are known as energy bands. So if the atom is an isolated atom, then it has got energy levels and they are discrete in nature. But once many atoms come close together, what is happening is the outermost orbits, they come under influence of each other. Because of that influential energy, then some kind of perturbations or the disturbance in the levels occurs. And because of that, splitting of the energy level happens. And the energy levels, instead of being a single energy level, it forms bands of energy levels, which is known as energy bands. And here one simple picture is displayed to make these points clear. You can imagine that the central part is a nucleus, which contains protons and the neutrons. And after that, what we have is the first energy level. Okay, and this first energy level or the cation, it can have two electrons. Two electrons. Okay, because its capacity is 2n square and n is equal to 1. Therefore, 2 into 1, 2 electrons. Similarly, this is next one is the second energy level. It can hold 8 electrons. Okay. Similarly, the third energy level, it can hold a maximum 18 electrons. Okay, and distributed over 9 different orbitals. This we will see when we take up the energy band diagrams in a detail. Okay. So these are the different energy levels. Okay, and this is always the outermost orbits where these okay, perturbations occurs due to mixing of the atoms. So in the energy bands topic, we will see, we will take up that in detail, how to draw the energy levels and how these levels they will form the different energy bands. Now, uh, starting with the bonding forces in the solids. Okay. So here, uh, the interaction of electrons, okay, the interaction of electrons in the neighboring atoms of a solid is an important function. Okay, so which holds the crystal together. So what was the statement? The interaction of electrons in the neighboring atoms of a solid, it serves an important function. What is that important function? Is it holds the crystal together. Okay, so therefore we find different types of bondings in the solids. So this is because of what? This is because of the what? The interaction of electrons with the neighboring atoms. Okay, it not only the main function of that kind of interaction is it holds the crystal together. And how it holds the crystal together? It is because of the bondings that are formed between the atoms. So we will see now in this particular topic what are the various bonding forces that are present in the solids. Okay. So to name a few, so we have the ionic bonding, then covalent bonding, metallic bonding, and the mixed bonding. So here, the two pictures are displayed. One is for the ionic bonding by taking example of NaCl sodium chloride, and covalent bonding in case of silicon. So considering this ionic bonding, what are the features of ionic bonding? So here you find Na plus and Cl minus. Okay, so let us know what are these two. Okay, so the reason is the ions. So we write them as Na plus and Cl minus because they are the ions. They are the charged particles. So ion is nothing but the compounds composed of metals and non-metals. They contain charged particles. So these charged particles are known as the ions. So for example, the example is a sodium chloride. So in a sodium chloride, the positively charged ions are sodium and negatively charged ions are nothing but chloride. Okay? So therefore, when you take up the ionic bonding example in case of sodium chloride, okay, so this is what is a slice through a NaCl crystal. Okay, a slice is cut. When a NaCl crystal is cut into slice, then this is what is the visibility. So you just observe first. Okay? Na plus, it is surrounded by Cl minus, Cl minus, Cl minus, and Cl minus. But this is only a front view. Okay, so actually, in this ionic bonding or in the ionic bonding lattice, it is called ionic bonding lattice. Each Na sodium is surrounded by 6 nearest neighbor chloride atoms. Okay, so actually their number is 6 that I will display in the next diagram. So here this is what some of here. This shows ionic bonding in NaCl. Okay. So here assume that the center one green, this is sodium Na, and whatever are in golden color, they are nothing but the chloride ions. Okay, so observe that to this central sodium ion Na, okay, so there are 6 chloride, 1, 2, horizontally 3 and 4, then 5 and 6. Okay, so therefore each Na in this particular lattice, NaCl lattice, each Na atom is surrounded by six nearest neighboring chloride atoms. Okay, so this is what is the structure. But to write in your papers, you can use a previous picture only. So this picture only, that is ionic bonding in sodium chloride. Okay, so here you will see that as it's a cross sectional view, only four. But exactly the 3D picture, it shows Na lattice, NaCl lattice. Each Na is surrounded by 6 Cl atoms. Okay, so therefore, what are the observations from this particular structure are? Okay, that is particularly in this bonding. What is the speciality? All electrons are tightly bound to the atoms. Okay, so in a NaCl ionic bonding, the very first feature is all electrons are tightly bound to the atoms. And once the electron exchanges have been made between Na and Cl atoms, okay, the outer orbits of all atoms are completely filled. Okay, so once electron exchanges have been made between Na and Cl atoms, the outer, outermost orbits of all atoms are completely filled. Okay, so no loosely bound electrons. That is what is one feature. Okay, so hence NaCl is a good insulator. So why this 6 chlorine? This is because, okay, so always the number of electrons that are exchanged is in such a pattern so as to complete an orbit. Now in this, by borrowing 6 Cl, okay, that the orbit is completed. Okay, so if at all, if any one electron is left as an additional electron, then it will act as a free electron. But here in NaCl, okay, the orbit is completed with 6. Okay, so therefore there are no loosely bound electrons and the shell is completely filled. So therefore, as there are no additional electrons or loosely bound electrons, NaCl acts as a good insulator. So these are what important features of a NaCl lattice. Similarly, in another type of bonding, covalent bonding, the examples for this bonding are, okay, so in germanium, silicon and carbon lattice. Okay. So here I have shown the carbon lattice structure. Now in this, how the solids are formed is each atom, either maybe in a germanium, silicon or carbon, okay, each atom it is surrounded by four nearest neighbors. Okay, so each with four electrons in the outermost orbits, the outermost orbits. Okay. So if these crystals, in these particular crystals, like germanium, silicon or carbon, okay, they share valence electrons with its four neighbors. Okay, so with the sharing is done with the four neighbors, and whatever the bonding forces arise, okay, they are due to the interaction between the shared electrons. So that is the force that exists, which is known as the bonding force between the atoms, and that is because of the shared electrons. So this particular structure, this is known as the covalent bonding. Now in this, okay, so as in case of ionic crystals, so here also we find there are no free electrons available, okay, in the lattice structure. So therefore, by this reasoning, that is, as no free electrons are available, they are known as the insulators. Okay, but an electron can be thermally or optimally excited out of a covalent bond, and hence it becomes free to participate in the conduction. And this is an important feature that is found in the semiconductors. That is, while forming the covalent bond, due to sharing with the surrounding four nearest neighbors, there will not be any loosely bound electrons. Okay, in that sense, it is an insulator. Okay, but it is easily, an electron can be taken away from the covalent bond, and thereby the particular thing can be put into conduction, or it can be made to participate in the conduction, and that's why it forms an important feature of the uh, semiconductors. Okay, and that taking out of an electron, that happens because of thermal excitation or optical excitation. It's a semiconductor. It is neither a completely conductor or it is an insulator like NaCl. Okay, its conductivity is in between a, an insulator and a conductor. Okay, and easily it can be put into conduction. So that is what is the feature of this covalent bonds. Now going to one more type, that is metallic bonding. In metals, how the bonding is present. So in metal atom, the feature is the outer shell is only partially filled. Okay, usually not more than 3 electrons are found. Okay, so this is what shows the metal ions. And these red color dots, these are nothing but free electrons from outer shells of metal atoms. So in metallic bonding, what is the feature is the outermost shell is not completely filled. If it is completely filled, then it will start acting like a NaCl. Okay, and once it becomes similar to NaCl, its behavior is like an insulator only. But metals, the outermost orbit is only partially filled, and that too, why it is partially filled? Because there are no more than 3 electrons in the outermost orbits. So you can imagine that each particular atom will give three free electrons in the outermost orbit. Okay, and these loosely bound electrons, they are responsible for higher conductivity. Okay, now these electrons were not found either in the previous two cases. Okay, and first of all, in NaCl, it was completely a bond. There were no free electrons. And even in case of the germanium silicon, okay, so because of covalent bonding, sharing was there. Therefore, there were no free electrons, but they can be excited. But in case of metal bonding, uh, the outermost shell, it contains loosely bound electrons. So, and that becomes the reason for higher conductivity of the metals. Okay, and also in this picture you can see that these atoms. Okay, so how the free electrons are there, and here at one more point is that, so in the metal, the outermost or the outer electron of each alkali atom contributes to crystal forming sea of electrons. That is obvious. Okay. Assume that each atom gives out 3. So therefore, for an entire structure, uh, for it looks like a sea of electrons, and that is visible from this second picture. Okay. So whatever we find here, red dots, they are all the free electrons, and the forces holding the lattice together. Okay, so they arise from positive ion core and surrounding the free electrons. So these are the important points that we have to write in case of metallic bondings. Okay, so in NaCl, how it is, and in the previous covalent bonding, because of the sharing, we don't find any free electrons. But due to thermal or optical excitation, free electrons can be made to come out, and that's why it behaves like a semiconductor. It is. Okay, basically it is like a insulator only. Okay, but it can be put into conduction very easily. In metal, it is because of the structure itself, there are a lot of free electrons available, and because of that, the conduction happens very easily. So the energy bands, whatever I was discussing in the beginning, okay? So it has some complex structures like this. So that we will take up uh, the next section. Okay, and there is one more category. What was that? The mixed bonding. Here I have not included in that. So in the mixed bonding, it is found in some compound semiconductors like gallium arsenide. Okay, they have a mixed kind of bonding in which both ionic and covalent bonding forces participate. Okay, why it is called mixed bonding? Because it exhibits both ionic bonding as well as covalent bonding. So such a feature is called known as the mixed bond. So these are the three kinds of bonding that are to be written with diagrams as well as explanation. So for a mixed bonding, that is sufficient. One note you write it. So this is all about bondings. Maybe in even basic electronics also, if you have some information, that information also you can add. Okay. So therefore, in order to conclude this, so energy bands, they are nothing but whenever isolated atoms are brought together to form a solid, then various interactions will occur between the neighboring atoms. And the forces of attraction and repulsion between the atoms will find a balance at the proper interatomic spacing for the crystal. And in that particular process, so important changes will take place in the electron energy level configurations. Okay, so and these changes will result in varied electrical properties of the solids. So in isolated atoms, we find energy levels, but whenever isolated atoms are brought together to form the solid, then various interactions will occur between atoms themselves. Okay, so what are those interactions? The interactions are nothing but splitting the energy levels, forming the different energy bands. There may be attraction, there may be repulsion, and finally there will be a kind of balancing action. Okay, so totally they are going to change the characteristics. So important changes with respect to electron energy level configurations is going to happen. Okay, and because of this we find various electrical properties of the solids. Okay, so therefore the electrical properties of the solids are mainly because of the interactions that happen with respect to energy levels and energy bands of the atoms. So in the next session, we will see what is this linear combination of atomic orbitals. So how atomic orbitals can be linearly combined. Graphically, how are we going to represent? So I'll take up in the next hour. So this week I have handled the algebra classes. So maybe next week we will inform you which is what the topic.